Hello. So this lecture is on PID control. It's actually going to be the first of 4 lectures on PID control, which is the final topic for the course. So the type of control structure that you've looked at so far is actually called P control or proportional control. So with this control structure, we have the system G, and then we have a feedback loop where the output of the system, the measured output, is compared with a reference or a demand signal. This comparison gives an error, and then the error is scaled by a gain Kp to produce the input to the system U. So with this type of controller, the input to the system U is proportional to the error. So the advantage of this type of control is that it's very simple and it's easy to set up usually in terms of practical implementation. And also there's many methods for selecting or tuning the value of the gain Kp. And the method that we've looked at before as an example is the root locus method. What are the disadvantages or drawbacks with just using P control? Well, one, it can be difficult to get the error E to go to 0, even when the reference input is constant. And also it can be difficult to get good step response performance when the system G is not a first order system. So for example, if G is a second order or a third order system, then using proportional control, it may not be possible to get good performance metrics for the step response. Okay, so just to sort of review what we can do or the behavior that we can get when using P control, we're going to do an example which we've done before, which is the water tank system, but we're also going to try to look at maybe what are the limitations of using P control for this type of system. So if we take the standard model for the water flow into and out of a water tank, so the rate of change of the height of fluid relates or depends on the flow rate into the tank, Q in, and the flow rate out of the tank, Q out. And the flow out of the tank also will depend on the height. So for this simple model, we can say that the rate of flow, the volume flow rate out of the tank is proportional to the height. We use a coefficient of 0.4 for this example. If we substitute that into the governing equation, we get a differential equation that relates the height of water in the tank to the volume flow rate of water going into the tank. So we can transform this equation to the Laplace domain to get the transfer function for the system that relates the height of fluid, height of water, to the flow rate going into the tank. So if we want to control the height of fluid in the tank, we can set up a feedback control system. So the idea is that we use a sensor which is able to measure the height of fluid in the tank. For example, a pressure sensor would work. The signal then from the sensor goes into the control box or the controller electronics, and then the controller electronics sends an actuation signal to vary or can vary the flow, the opening, closing of the valve so that we can set the flow rate through the valve. So we can set the value of Q in through the controller. So if we put these three components together, the sensor, the controller, and the valve, then we can create a simple model which gives us the feedback structure shown in the block diagram. So in this case, if we set up the controller electronics correctly, we can get the valve, the opening of the valve, to give a flow rate which is proportional to the error, right? Proportional to the difference between the reference set value for the height and the actual measured height. So this is the basic model structure for the feedback control system. And if we want to analyze the behavior of the system, so to find out how the height of fluid in the tank might change over time, then we can calculate the closed loop transfer function, which is given by this equation here at the bottom. So this transfer function now relates the reference signal R to the height of fluid, the height of water H. And of course this transfer function now depends on the value of Kp. So Kp is the proportional gain for the controller. Okay, so in this slide we're going to look at two cases where the response of the system is examined for two different values or two different settings for the controller gain. The first case is with Kp equals 1 and the second case is Kp equals 5. So initially the height of fluid is 0, so the tank is initially empty. The initial value of H is 0, and we can calculate the response of the system if the reference value is a constant value of 3 meters. So R is set to 3. So the Laplace transform of the input is going to be 3 over S. And then, okay, we could calculate the H by multiplying the transfer function by R and doing the inverse transform. But here we just look at the animation. In the animation, we do not, the picture here does not include the control system components, but obviously they are operating. So we can see that the height of fluid in the tank will increase due to the action of the control system. And if we plot the graph showing how the input and output change over time. So the dashed line here is the reference R, and the blue line is the height of fluid. So the height increases over time and converges to a steady value. So you can see that after about 10 seconds, the height of fluid reaches a constant value of around 2.2. And so in the steady state, there's quite a large error or difference between the reference value and the actual height H. So if we do the same, look at the same situation again, but with the controller gain now increased. So now Kp is equal to 5. Okay, so we get a similar behavior. The height of fluid increases over time, but we can see two important differences between the first case and the second case. One is that in the second case, the height of fluid reaches a steady value more quickly, so the system responds more quickly. In this case, the settling time of the system is around 2 seconds. So the height increases more quickly, and the second difference, or the second main difference, is that the steady state error is reduced. So we can see that with p-control we can influence the speed of response, but we can also influence the size of steady-state error, and generally for the case of a first-order system, and the water tank is a first-order system, then we can reduce the steady-state error and we can reduce the settling time by increasing the value of Kp. But obviously there's still some something that's not so this is still not ideal, because although Kp reduces the steady state error, we do not actually get zero steady state error, which ideally we would like to have no error. So we could try to make the error smaller by increasing the value of K further, but to get a very small error we'd need a very large value of Kp, and this may not be physically possible. And the reason for this is that if we have a very large value of Kp, it means that for a small error we would require the valve to give a very large flow rate, and of course the maximum flow rate through the valve will be limited by the size of the valve. So if we try to get a very large flow rate, we'll find that the flow rate is no longer proportional to the error, so we'd start to introduce saturation effect and nonlinear effects, which means that the behavior of the control system would be harder to predict. So ideally we don't want to have too large a value of Kp, and this is also true not just for the water tank system but for other systems as well. There's going to be a physical limitation why a very high controller gain is not physically realistic. So is there another way to reduce or get the steady state error to go to zero? Well, one possible method is to use a pre-scaling of the reference R. So this is like introducing a correction factor. So R is scaled by a constant A, and the idea is that if you choose the value of A correctly, then we can get a improvement in the input-output behavior in the steady state. So the idea is that there's going to be some value of A, so that in the steady state the value of the output H will be equal to the value of the reference R. So we can find the required value of A by looking at the closed loop transfer function. In this case the transfer function is modified, so it includes the factor A, and then if we want the steady state gain of the system now to equal 1, then it means that we can find the required value of A, right, the steady state gain of the system we obtain by setting S to 0, and if we set S to 0, we get this. Okay, so that's the steady state gain of the closed loop system, and then to get a steady state gain of 1, which means H equals R in the steady state, this has to be equal to 1. So then we could solve for A, and then the value of A can be chosen to match the value of Kp. So this would work. So we can find the appropriate value of A. But is there a drawback of this approach? Well, one problem that might occur with this approach is that maybe we don't know exactly what the transfer function of the system is, or maybe the characteristics of the system will change over time. And for this to work properly, correctly, we need to know the system transfer function exactly. Okay, so an alternative approach, and usually a better approach for reducing steady state error, or even achieving zero steady state error, is to use a new type of controller. So the type of control that we're going to look at here is called a PI control. So the key difference here is that now the controller is no longer just a simple gain, but the controller actually has a transfer function. So the controller transfer function is going to be a function of S, and that means that the controller is actually now going to be a dynamic system. So for PI control or PI controller, the transfer function of the controller combines two terms. So as you can see, the transfer function has a term Kp, it's the same as before, so Kp is the proportional term, but now we add another term which is Ki over S. So this is called the integral term. So Ki is another controller gain which we can choose the value of as we want, and Ki is called the integral gain. So P is the proportional gain, Kp is the proportional gain, and Ki is the integral gain. So we can combine the two terms to get a fractional transfer function, and you can see that the key thing here is that the controller transfer function, the denominator contains an S on its own, and the numerator has a term Kp times S and plus Ki. Okay, so if we want to implement this dynamic controller, we can do so by creating the required electronic hardware. So this could be an analog circuit with op-amps, resistors, capacitors, or it could be created using a digital microcontroller. And as with the proportional controller, we need to choose or tune the values of the controller gains. But in this case, we've got two gains that we can vary independently. So we can choose Kp, we can choose Ki, and the value should be set in order to get the best performance that we can. But the suitable values for Kp and Ki will depend on the system, so they'll depend on the plant G and the characteristics of the transfer function of the plant. Okay, so to show the advantage of using PI control, we're going to look at another example. Again, this is the water tank system, but there's a key difference here, which is that the water tank now has an additional flow into the tank, which is QD. So QD is an additional input flow, but QD is going to be unknown, or something that the flow rate cannot be changed, it cannot be regulated, so it behaves like an external disturbance. So something that affects the height of fluid will affect the height of fluid in the tank, but which we can't do anything about, at least not directly. So the idea is now we want to use the PI controller to kind of compensate for the effect of the additional flow into the tank. So in this case, the governing equation for the system is going to be modified. So on the right side of the equation, we've got Qin, which depends on the feedback control, but we've also got an additional term, Qd. So in this case, the block diagram for the closed loop system has the form shown at the bottom here. So we have the feedback loop, and the reference here is scaled by a constant A, so this will help to correct for steady state error, and then the error signal goes into the controller. In this case, the controller is a PI controller, so the transfer function of the controller is K, and the output of the controller is the flow rate Qin, so that's the flow through the valve which is regulated by the controller. And then we've got the additional input here, which is the external flow rate Qd. So in this case, the height of fluid in the tank will depend on the reference, but it will also depend on the input Qd. Okay, so we're going to look at two different cases, but in this case, the first case, the controller is a proportional controller, and in the second case, the controller is a PI, so proportional plus integral controller. So the first case, we pick a value of Kp, which is the same as the previous example, so Kp is equal to 5, but now we include the prescaling coefficient, which is set to 1.08. So with this value of A, we find that the steady state gain that goes from R to H will be equal to 1. So what we find, okay, this shows the system structure, block diagram, and we're going to show the animation now. So initially the level of the height of water is 0, and then you see that the height increases to match R, but then a short time later we have some extra flow, so Qd then becomes non-zero, and the effect of Qd is to create an additional flow rate into the tank, and the controller here doesn't actually know anything about the additional flow coming into the tank, and so what happens is the height of fluid then increases and we end up with a steady state error. So in this case, the steady state error is not due to the so it's not due to any problem with the setting of the P control, it's just due to the fact that we've got this extra flow coming into the tank. Okay, so that just shows the animation again, and then if we plot the graph, so here we've got 3 variables or 3 signals. So the dashed line is the reference, the blue line is the height, and then the red line is the additional flow, Qd. So you can see that initially when the extra flow Qd is 0, the height increases to match the reference to 3, but then when the extra flow into the tank starts, we get an increase in the height, and so we have in a steady state the height of fluid is too high. Okay, so if we change our controller to a PI controller, okay, so the block diagram for the control system is shown here at the bottom. So we keep Kp equal to 5, and for this example Ki is set to 15. Notice in this case we don't include the prescaling as it's not actually necessary. So the idea is that the I term in the controller will now help to keep the steady state error 0. So if we do the same simulation or calculate the same the response for the same situation, so initially the tank is empty, and then initially the extra flow into the tank is 0, but after a short time the QD will become non-zero. So if we just show the animation, so the fluid height of water increases to match the reference. When the extra flow comes into the tank, that creates a disturbance, and you can see there's then some fluctuation in the height of fluid. But after a short time, the fluid settles back down so that the height of fluid then matches the reference. Okay. So if we look at the graphs in this case, you can see that there's some difference initially, that the height of fluid shows a rapid increase. There's some overshoot, but the height settles so that there's 0 steady state error. And then after 5 seconds, the extra flow comes in. Again, the height increases, but then settles back down. So you can see that with the PI controller, we have 0 steady state error, even though we have the extra flow coming into the tank. And this is due to the extra sort of control component in the control input, which comes from the integral term in the controller transfer function. Okay, so why does the PI control, why is it able to make the steady state error go to 0? Well, if we look at the mathematics, so if we look at the transfer function, we find that the steady state error is 0 because the PI controller transfer function has a pole at s equals 0. So the transfer function, you can see, has an s on the denominator, and so it means the controller has a pole at the origin of the complex plane. So this is the key characteristic of the PI controller transfer function. And what it means is that if you calculate the closed loop transfer function of the system, we find that the s in the denominator of the controller transfer function ends up in the numerator of the closed loop transfer function. And so the closed loop transfer function has a 0 at the origin of the complex plane. It has an s in the numerator, and this means that in the steady state the error for a step input will be 0, and you can show this using the final value theorem. When we take the limit as s goes to 0, we find that also the steady state error goes to 0. So the details of the mathematics are given in the extra slide at the end of the lecture. So let's just look again at the property or the transfer function of the PI controller. So the transfer function of the controller defines the control law. So the PI controller, the transfer function, is equal to the output divided by the input. So for the controller, the output is U and the input is E. And so U divided by E in the Laplace domain is equal to Kp plus Ki over S. So we can write the control law, meaning that we can write U as a function of E. Okay, so the control input can be written as a function of the error. If we write it in the control law in the Laplace domain, we get this equation here. So we have a term which is Kp times E, so that's the proportional term. So there's a component in the control signal which is proportional to the error, plus this term Ki times 1 over S times E. So here in the Laplace domain we've got the error divided by S times Ki. So this is an integral term, and to understand why this is why we call this an integral term, you can see that if we take the inverse transform, so if we change the control law from the Laplace domain to the time domain, then the term 1 over S gives us this integral term in the time domain. So here you can see that the control input U has a component proportional to E, but it has another component which is proportional to the integral of E over time. So we're integrating the error over time from 0 to the current time. So in a way, this is like the area under the graph of E. And this means that if the error is non-zero, then U is going to keep increasing until the error becomes 0. So to summarize, the control input depends not only on the current value of the error, but also to the integral of the error over time. And so this means that if E is not 0, then U is not constant. And so we find that in the steady state, to get steady state behavior, that means that the only way the input U can be constant is if the error is 0. And therefore we can conclude that the only way that the output Y can be constant is if the error also is 0. Okay, so obviously if we're using a PI controller, we still have to find a way to choose suitable values for the gains, the controller gains. And in this case, we've got two gains. We've got Ki and Kp, so we have to find suitable values for both gains. And we're going to look at two key methods. The first method is to use what we call pole placement. So this is, we're only going to look at cases or use this method for cases with first order systems. So the idea is that for a first order system, if we add a PI controller, then the overall system, so the closed loop system, then becomes a second order system. And so the closed loop characteristic equation is second order, and it depends also on Ki and Kp. So we've got two poles for the closed loop system. We've got two gains that we can choose, and so the idea is that we can then set the value of Ki and Kp to give us the values of the closed loop poles that we want. So in fact, Ki and Kp can be chosen to place the poles of the closed loop system at any desired location. So we can place the poles at any points that we want on the complex plane. So that's method one. The other method, method two, is to use a root locus analysis, and this method can be applied not just to first order systems, but in fact to any systems with any order, so second order, third order systems. We can sketch the root locus to help us choose values for the controller gains. So to do a root locus, the root locus will depend on the poles and zeros of the open loop system, and with a PI controller, okay, we're going to have some poles and zeros which come from G. So we have poles and zeros that come from the plant, but we also have poles and zeros which come from the controller. So a PI controller, if you look at the transfer function, you can see that the PI controller has 1 0 and 1 pole at s equals 0. So you can see that the pole for the controller transfer function is always at s equals 0, but the 0 of the transfer function depends on the value of the 0 depends on the ratio ki over kp. So we can sort of set the value of the controller 0 by setting the value for the ratio, so the value of ki divided by kp. So if we fix the value of the 0, that means we're fixing the ratio ki over kp, then we can plot a root locus for which would be for changing the value of kp. So to sketch a root locus, we first fix the controller 0, so we fix the ratio of ki over kp, and then we can sketch the root locus based on the pole 0 map of the open loop system, which now includes both g and k. And this way we can use the root locus to help us try and choose a suitable value for kp. And then the value of ki comes from the value of kp because we've already fixed the ratio of ki over kp. So I'm going to do an example problem where we apply method 1. So here we consider applying a PI controller with the water tank system. So we're controlling the level of water in the tank with the feedback control loop as shown in the block diagram. So the question is to determine the values of kp and ki such that the closed loop system has a natural frequency of 4 radians per second and is critically damped, which means that the damping ratio should be equal to 1. So the method that we use here, we can first write down the transfer function for the controller, which you can see. Okay, we can write down also the transfer function for the plant, or the system that we're controlling, and then for the closed loop system, the characteristic equation is going to be given by this equation here. So this is the case for any feedback control system where there's a system G and with transfer function G and a controller with transfer function K. Then with the negative feedback, the characteristic equation is going to be 1 plus K times G equal to 0. So if we substitute the transfer functions K and G, we have the equation at the bottom here. And then we can multiply both sides of that equation by the denominators of the transfer functions so that we have an equation that looks more like a polynomial in S. Okay, so we have the characteristic equation, which we can now try to simplify. So if we multiply out the brackets on the left side of the equation, then we have this polynomial where we can collect terms, and okay, we now see that we have a quadratic equation in S, and we can clearly see the coefficients for the terms in S squared, S, and the constant term. Now to find the values for Kp and Ki, we need to compare this equation with the standard form for a characteristic equation of a second order system, which will be in terms of the damping ratio and the natural frequency. So you can see we've got a slight difference between our equation and the standard one, because the standard equation, the coefficient in front of the coefficient for the s squared terms should be 1, whereas the equation we have here, it's a 2. So first we multiply the equation by half so that we end up with a unity coefficient for the s squared. Now the two equations that we have here are in the same form, and we can compare coefficients directly for the two equations. So if we do that, okay, if we equate the coefficients for the terms in S, we get this first equation. If we equate the terms for the constant here, so these two terms, then we get another equation which involves Ki. So the first equation here now involves Kp, and we can rearrange that to get a formula for the value of Kp in terms of the damping ratio and natural frequency. And we can do the same thing with the second equation, we get a formula for Ki. So the information in the question told us that the target for the closed loop system was to achieve a natural frequency of 4 and damping ratio of 1. So all we have to do now is to substitute those values into the two equations. So we find the value for Kp is going to be 15.6, and then the value for Ki will be 32. Okay, and then to finish we can write down the complete transfer function for the controller. So we have our solution for the controller. So this is the closed loop control system now, including the solution for the PI controller, and then okay, to check if the controller works well, if we have got a good solution, we should calculate or simulate the response of the system. So if we do that now, we consider the same situation as we did previously, where we have initially empty tank and we have a target level of 3, and we also have an additional disturbance, extra flow coming into the tank, which starts after 5 seconds. So if we calculate the response, and the animation here shows what happens, you can see that the performance of the control system is quite good. So we get initially the height of fluid increases quickly, we get a small amount of overshoot, but there's no oscillation in the level of the tank, and the settling time is quite short. And then also, although we have this extra flow coming into the tank, you can see that this causes a small error, but then the error reduces back to 0. So we've got a good solution here for the PI controller. So the second example problem that we're going to do involves using method 2. Here we're applying a PI controller together with a system which is an electric motor with a load. And note that in this case the system is a second order system, so we cannot apply the first method, method 1 in this case, which method 1 is only suitable for first order systems. So the output here is the speed of the motor, omega, and the input is the torque. So there's two components to the torque, one which comes from the controller and another component which is external disturbance. and the controller acts on the error, which is the difference between the reference value for the motor speed and the actual value for the motor speed. So the problem is split into two parts. So for part A, it says fix the controller 0 at -3 and sketch the root locus for changing value of Kp. And part B says find the value of Kp such that the two dominant poles, which are those nearest the imaginary axis, are critically damped. So to sketch the root locus, we start by writing down the transfer function of the open loop system. So we call this transfer function L, which is equal to K, the controller transfer function, times G, the system transfer function. And then we can rewrite the open loop transfer function in pole 0 form. So for the numerator here, we take out a factor Kp. So we can then clearly see the 0, the factor involving the 0, which comes from the controller. And then for the denominator, okay, we have a pole at s equals 0 from the controller, and then two other poles come from the plant transfer function. So we can factorize the denominator of the plant transfer function here, and okay, we see that we have two poles from the plant which are at -1 and -2 and -10. So to sketch the root locus, we can first just write down the values for the zeros and poles of the open loop transfer function. So you can see that the value of the 0, Z1, is going to be minus Ki divided by Kp, and it says in the question to set the value of the 0 of the controller to -3. So here we've done that. And then for the poles, okay, we've got three poles with values 0, -1 and -10. So we can then start to construct the root locus diagram by sketching or showing on the diagram the pole 0 map for the open loop system. So you can see we've got the open loop system has a pole at 0, -1 and -10, and then a 0 at -3. So then to continue to construct the root locus, we can use rule 2, which tells us that there will be a branch of the locus between the two poles here on the left, and then there will be another branch of the locus between the 0 and the pole. So rule 2 allows us to complete the branches of the locus that lie on the real axis, and then to continue we can go to rule 3. So rule 3 tells us about the location and number of asymptotes. So the number of asymptotes is equal to n minus m. So n is the number of poles and of the open loop transfer function, and m is the number of zeros. So here n is 3, m is 1, so we're going to have two asymptotes. And to add the asymptotes to the diagram, we need also to know where the center of asymptotes is. So the center of asymptotes is basically the starting point for drawing the asymptotes, and the formula for the center of asymptotes is shown here. So we sum the poles, subtract the sum of the zeros, and then divide by 2. And in this case we find that the value for the center of asymptotes is -4. So we can now add the asymptotes to the diagram. So if we have two asymptotes, we know that the direction of the asymptotes, one asymptote goes straight up and the other asymptote goes straight down. and the asymptotes, two asymptotes start at the -4 point here, and in order to complete the root locus diagram, we have to draw the branches that tend to approach the two asymptotes. So we can see that as we've got two poles next to each other here, with the locus between the two poles, we must have a breakaway point between the two poles here, and then one branch which breaks away upwards will tend to the asymptote at the top, and then the other branch which breaks away downwards will tend to the other asymptote that goes vertically down. So this pretty much completes the diagram or the sketch of the root locus. Of course, we should add some arrows to show the directions that the poles move in for increasing KP. So just to summarize, to get the root locus diagram, we fix the value of the controller 0. So we fix the ratio of Ki over Kp to 3, so that the controller 0 is fixed at this location here, and that allows us to construct the root locus for changing the value of Kp. So you can see that as we increase Kp, the two poles on the right side here will follow the branches, which become complex here and here, and this pole at -10 will move to the right, and for very large Kp will approach the value of the open loop 0. So that completes part A of the question, and turning to part B, if you remember, we now need to find the value of Kp so that the two dominant poles, which are the poles which are going to be closest to the imaginary axis, so the two poles that start here and here, we have to find the value of Kp so that these two poles are critically damped. So that means that the two poles must have equal value, which means that the two poles would both be at the breakaway point here. And remember, for this system it's a third order system, so we've actually always got three poles, and if the two poles on the right are at the breakaway point, the pole here on the left will be somewhere along the branch here, but we don't know exactly where. But we can now try to find the exact location of the breakaway point and the corresponding value of Kp. So to find the breakaway point, we need to use the formula, which is given in Rule 4. So the formula involves the derivative of L, and we can solve to find the solutions for S which correspond to the breakaway point. So I'm not going to go through the details of using the formula now. So if we've done the calculations correctly, if we've applied Rule 4, we find that the solution for the breakaway point is the value minus 0.537. And then if we substitute this value of S back into the characteristic equation, we can find the corresponding value of Kp, which is 0.955. And then remember that we've fixed the ratio Ki divided by Kp. We fixed that ratio to 3, so it means that we can solve to find Ki by multiplying Kp times 3. So the value of ki is 2.985. So these are the two values for the controller gain. This gives us the solution that we need to place two of the closed loop poles at the breakaway point, so to give them the same value of minus 0.537. So we can also solve the problem and plot the root locus using MATLAB or Octave. So to plot a root locus in MATLAB or Octave, we use the command rlocus, and the arguments that we have to provide when we're using this command are the values of the coefficients for the numerator and denominator of the transfer function of the open loop system. So you can see that, okay, the 1 and 3 here, these values are the coefficients for the numerator of the transfer function, and then the four values here are the coefficients for the denominator of the transfer function here. So this one is the constant coefficient, this is the coefficient for s, this is for s squared, and this is for s cubed. Okay, so this is the result for using the command. We generate the figure shown here, and then this shows obviously the root locus diagram, the same as or similar to what we sketched earlier, and by clicking on the locus we can find the value of the breakaway point and the corresponding value of the gain Kp. So this is a good way to check the solution is correct, although obviously in this case we can calculate the solution ourselves algebraically. Okay, there's one final sort of extra question here, just something to think about in terms of understanding and interpreting the root locus. So does this root locus suggest any performance limitations when applying PI control with a second order system? And it's asking, is it difficult to get good pole placement? Well, that depends in a way what you want to achieve, but if you want the system to have a short settling time, then yes, maybe it's not possible to get a very short settling time with the PI controller here, and the reason for that is that the two poles on the right here, they cannot be shifted far away from the imaginary axis. So to get a fast response, to give the closed loop system a short settling time, we'd need to shift these poles further from the imaginary axis. And you can also see that if we try to increase Kp further, then the poles here become complex, so they become underdamped, and for large values of Kp, the damping ratio is going to become quite small as the poles move further and further from the real axis. So although we can get a reasonable response here with applying the PI controller to this second order system, we are never going, there's a limitation to how fast we can make the system respond when using a PI controller. So that completes the lecture on PI control. There are some extra slides that you can look at in your own time, which goes over some of the details, some of the mathematical details that are we didn't go into in the lecture.